Uh-huh. Okay, yeah. So let's do that. So just for a second, I'll just share the thing once so that we can confirm that this is the paper that everybody is looking at. Yeah, mock test 3. Oh yeah, because I have to reshare it. Yeah, but just to confirm it, because I had changed some of the questions. So this is the mock test we are going to discuss. We'll see how much we can. I can, because I don't remember when I made these questions long time back. So yeah, are these the questions that you guys have? Okay, is it right? Okay, so then let's move forward. I hope that everybody who is here has tried the questions. If you have not tried the questions, then it will not be useful. Okay, so yeah, let me now again go back to the screen, and let's go to problem number 9 you want to discuss. Okay, so let's see. So this is, I'll just write the heading. This is mock. So which one should we start with? 6. Okay, so let's just start with 6, and then we will do 9 after that. Okay, so let's start with 6. Okay, we'll do 9 after 6. Okay, so then let's do it. Okay, so 6 is, so we are looking at a convex function. Okay. So f is a convex function, and we want to prove that something good about convex function. Yes. Yeah, sorry. Maybe I did not need to present the paper. So, yeah. But anyways, so what you're looking at, f is a convex function, and we want to prove good properties about this. And you essentially want to prove that there is a point where the left and right derivatives are of opposite signs. Okay, so we want to show that there exists x naught such that the so maybe I can say this, yeah, this times the right derivative times the left derivative at the same point is less than equal to 0. So left and right derivatives are, 1 second. So you are saying that this is not true. Yeah. Right. Yes. 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 But I did not write the strict inequality. So no, that is not correct. I did not write the strict inequality. But if the question might still be wrong, it is still wrong, I think. It's a counter. Yes. Yes. So I will add a condition. Okay. So the condition that I'm going to add is um, uh, at least one, at least, so minimum is attained. Sorry. Yeah. So minimum is attained um, inside, in the interior. Right? So the minimum is attained in the interior. So f is a convex function from 0, 1 to r, okay? And the minimum is attained in the interior. Then maybe this question, . 。 Yes. Otherwise, this question is not true, right? I mean, it could just be. Yeah. So let's think about this. Yeah. Mm-hmm. Okay. No, no, no. So we have to, there is something there. So you're saying that the minimum point is the point, right? That's fine. That's fine. But here the point is that if you take the minimum point, so let's say that x naught is the point where the minimum is at. And yes, I was basically having in mind a proper convex function. Not a convex function which is increasing, because well, that is convex. An increasing convex function is convex. That's fine, but that is not the convex I had in mind when I made the question. Okay, so that's how the flaw came. No, no. Let us see. Let us see. There is a subtle thing in that. No, no, that's right. But yeah, let me just draw this, and then I'll ask you to explain that. So the claim is, so let me first write the claim, because all of us seem to be making that claim, right? Because yeah, I mean, if f was differentiable, then by Rolle's theorem, both the derivatives are zero at that point, right? But f may not be differentiable. So claim is that um, at mhm, mhm, no, no, but a convex function will attain. Let's see. No, yeah, yeah. So claim it that at x naught equal to minimum of f, okay. Yeah, the okay. Think writing too much, right? One whole. So Adish, so you had a reasoning. Say that first. Uh-huh. Mm-hmm. F of x naught plus h. Okay. Oh yeah, yeah, you said that, but fine. That's fine. Okay. H. Okay. Limit h tends to 0 plus. Mhm, mhm. Yes, greater than equal to 0, not necessarily positive. Okay. Yeah, if the limit exists. And similarly, the left-hand derivative has to be lesser. Hmm? Yes, yes. Someone else saying something? Okay. But so everything just boils down to, so this is like a generalization of Rolle's theorem. You see, if it's differentiable, then this gives you the Rolle's theorem. Okay. But here, everything is now boiling down to showing that convex functions have one-sided derivatives. That now you have to show. Uh-huh. Mhm. Yeah, but in what form are you going to use? That really matters. Okay, so are you trying to prove that convex functions have one-sided derivatives? Like, no, but how do you know that the left-hand derivative even exists? That is where we are, right? Because otherwise we are done, right? Otherwise this reasoning is sufficient. Continuous है तो that doesn't mean that left derivative will exist, right? That is the point. In fact, but yeah, yeah, but still you have to show. You have to use convexity in a very strong way to show. So that's what we are trying to show. Otherwise, we don't want to use Jensen's inequality because this simple limit is itself is enough, right? So everything is now boiling down to showing that these have one-sided. And this I have done in the class earlier. I don't know if everybody was, if all of you were not there, but this is something that now you guys have to go back and try. Okay, so this is now show that convex functions, but I'll try to give some hints, or I'll ask if someone knows it. Have one-sided, right? Or let's say have left. Right derivative is the symmetric. This is the extremely important result. It is okay. So convex functions have have a left derivative. So does anybody know how do you prove this? Let me just write the. I will not discuss the proof in details now. Uh, hmm. I'm just writing the first definition first, and then maybe you can compare with this what you're saying and get new definition. So first of all, this is the definition. Okay, you can see it pictorially. I'm not explaining that, but this is the definition. Okay, pictorially you can see. Yeah. So yeah, then. Hmm. Is greater than or is, so what is the other thing you were saying? Last thing, sorry. F of y. Oh, this should be greater, right? No, this has to be greater. You can say yes, yes, yeah. So you have to use these kind of things. Okay, this is the basically the hint. Okay, this is true, and you can try to prove this from the definition of convexity. And more is true, but yeah. Essentially, the convexity means that as you're moving towards right, the 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 left derivative, I mean, this it's kind of increasing as slopes are increasing, and so that left derivative, I think, which you're going to make, the limit, that limit which you're going to take is the limit of an increasing function, and so left limit of an increasing function exists, that kind of thing. But this crude definition will not be very useful. Will not be the end thing. You have to make this kind of equivalent definition from that. Okay, now I'll leave it to you because you have to think. Okay, because there are some things in that. So please think that. Okay, that's where the problem comes from. And I have, yeah. So So question number 9, let me not do, because that is also just about convexity. Okay. And it is also having a similar reason. Okay. Then prove or give a counterexample, then this. No, so this also I had done in the class, I think, at some point, but in a different setting. Okay, so let's write it then. Yeah. So question number 9, this is basically what we are given is midpoint convexity. This is the name. You can relate to the name with the thing. So we are given midpoint convexity. What does it mean? It means that f of a plus f of b by 2. This is the average of the values at the endpoint. That should be greater. So it's like a weaker version of continuity is what we are given. Sorry, convexity, right? That given any 2 points on the curve, given any 2 points on the curve, if you take the, sorry, given any 2 points in the domain A and B, if you take the midpoint, yeah, and the average of the values at the endpoints is less than, sorry, more than the value at the average. Midpoint convexity. And the question really is asking is, does this imply convexity? Yeah, so does this imply does this imply convexity? So does this imply that this is going to be less than? That is the question. Was anybody able to do this? No, sign is okay. See? But I have also written in the reverse here, right? Like you take A and B. Oh, from the question you're saying. Oh, okay. That's a small. That forget. That doesn't matter. That's the same question. Do this question. That is midpoint concavity, midpoint. But these two are consistent, right? Right? These two are consistent, which I've written on the board. Then it is fine. I mean, that's the same question. It is minus. It is just a minus n. We'll get the proof or counterexample. That. Oh. Huh? Right. Yeah. Section formula. What is the section formula? Oh, okay. Yeah. So that point, no, but that point will just be section formula. Acha, yeah, from quadrant geometry. Acha, okay, that's section formula. So you take lambda a plus, but this is the point. No, this is the point. This is the point. Yeah. Mm-hmm. But why? That's what we want to prove. From the graph, but I just drew the graph. Yeah. It's not given it is convex, right? Graph I can draw anything. We believe it. No. It's not given it is convex. Yeah. What? Take all rational point. Yeah. So before you say more, yeah, that's yeah. This is not true. Okay, this is not true. And I had done this in class. I think that time Raghav I think was there, but He doesn't remember it now. But anyways, I don't know about the others. Yeah. So the point is it is not true. And so I'll ask Sampath to say what on this. Not true. Yeah. Yes, so Sampath. Yes, that also we had done. Right. Yeah. If it's continuous, then it is true. So Sampath, can you give a counter example? Uh, mhm. Right. Yes, it's close to the mid. Yeah. So midpoints of two rationals is rationals. Yeah. Yeah. Other points. Yeah. Yeah. So if so, you can. Okay. Yeah. That is not needed. Yeah. That's the point. But the point is that if you take the rationals and but then what should I define the function? So let's be more concrete. How should I define the function on the rationals? Right. We should do that. Okay. So let's write that. So take fx equal to, so the goal, idea is we want to make it that on all the rationals, this condition is satisfied, the first condition, and similarly on all the irrationals, that condition is satisfied. We want to make something like that. Okay, let's see. Okay, x plus just one is fine, x plus one is also fine. Yeah. But then what do we do after that? Because we need to ensure that on the irrationals also it is satisfied. Okay, you can put x plus 1 for the irrationals. So, but does it satisfy the midpoint convexity? That is the question. Does everybody? No, no, no. Something is off. Something looks off to me. This thing. No, no. You have to define, right? F is a convex function. So F is from an interval. Did I not write that? No, you can have equality. I'm fine with that because I've given, but I want, but obviously I have to define it everywhere. Otherwise, it's very simple. It's very different for a simple question. So yeah, you have to define it on everything, obviously. So if you're going to take it to be 1 on all the rationals and x plus 1 on all the irrationals, then hmm, it will go, yeah, it will go to a rational number. But is there a problem? No, there's no problem. So we are done. You should not make it 0. So x plus 1 is a problem. If you make it x plus 1, then why is 2 a problem? No, 2 is not a problem. I mean, not a problem means it's meeting the first condition. So this function meets the first condition. Okay, we have made sure that on all the irrationals it works and on all the rationals it works. We have kind of lifted the irrationals to a higher place. So even when you end up in rationals after average, it's fine. After average, it goes down. Good, it works, right? But how do you show this is not convex? It doesn't satisfy the second condition. Yes, yeah. We can take one rational and one irrational. Something. So then no. So let's be careful here. So if I take 1 and root 3, then why does it not work? Let's think. Or what lambda? So what should I take as lambda and so on? So that I'll just decrease the brightness of this guy. What will we do? Lambda has to be less than 1. Because that's so yeah, guys, everybody think, make a lambda so that it fails, second condition fails. So you don't want the average to become small. You don't want the value at the average or the left hand side. You do not want that to become small. So this part will be average is 1.5. Yes. No, I don't know. Average is this. It is not 1.5, but it is this. Okay, I mean with respect to lambda. Sorry. Something like that. Yeah, and that's right. So you can do. So you guys can check that, right? The point. No, why will it work? Because that's what we showed it. There's no contradiction for half, for lambda equal to half, right? And we made this example so that this works for lambda equal to half. So it is even work. So you have to pick a lambda in a way that this becomes bigger than this becomes bigger. So you have to just pick a lambda rational so that this becomes irrational. And if that is irrational, then the value is big, and so the inequality will not be satisfied. You can just No, but here we are going to take it with respect to lambda. Okay, you are saying about that only. Okay. But it is 2. So that is a So then how do you salvage this? It doesn't work. Yeah. So basically, wall construction doesn't work. So yeah, you have to. Yeah. So our construction, we made it so that when you take two rationals, it works. When you take two irrationals, it works. But when you take a rational and an irrational, two irrationals also it works. But when you take a rational and an irrational, then it does not seem to work. So then how do we rectify it? Let's think. No. I don't think it is true. But yeah, I have to give a counter example to say that. But without continuity, you can't. Uh-huh. Uh-huh. Then you can. Yeah, then you have made an example which will be midpoint. No, but you can make a counter example in this case also on all of R. So yeah, any ideas? How do you do this? So when you take two, yes. Midpoint convexity is nothing. Is this? It doesn't imply. You need continuity. So counter example should not be difficult. So we have I have done this earlier. Let's just think. Hmm, One more. That's what I was thinking. But then when sum of two irrationals become rational, then there is. Hmm. Okay. So yeah, but let's see if I take this. But then irrationals, the value is one. Irrational, the value is okay. Um, one, one second. Maybe you have to do it on a special subset of the rationals, like those with denominator 2 to the power n. But let's just give this thing one more chance. So if I'm taking two, so basically things like these. So as we are kind of thinking that this will not work. So yeah, this will not work here because this is going to be 1 because the values are 1, but this is going to be 2. This will not work. If I make the rationals big, then there is a problem in the conjugate case. And if I make the rationals small, and I cannot make them equal, but if I make the rationals small, then the rationals, then also it will not work. Yeah. So then this example, this way doesn't work. But let's basically see, how does midpoint convexity come? What does midpoint convexity let's see, things. This thing, if I take on, so I'm thinking that we take a special set because midpoint convexity kind of arises if you think about it. So you take those numbers which are of the form uh, uh, p by q, p by q, where q is a power of 2. Okay. If you take these kind of numbers, and they are also closed under average. Right? So maybe this is what somebody was saying in the beginning. If you take these kind of numbers, then these are also closed under the average, and then we can take the rest of the numbers. Right. Otherwise. Okay. So then does this work? So if two numbers are of this form, if A and B are of this form, then there is nothing to check because this is 2, 2, 2. But otherwise, if two numbers are but then yeah, so you can have, yeah, so that is a problem, right? So you could have two numbers which are not of this form, but then their sum would be of this form, right? And if their sum is of this form, then there is a problem. Yeah. So then again, same issue. If you change this, if you make this 1 and make this 2, also so this means that last time when I gave the counter example in the class sometime back, maybe it's a different way we did this, but that is probably wrong. Yeah. But yeah. No, that is also a problem. But here, but this does this work? This does not work, right? Because you can because if you take the numbers which are not of the form and of the form, then it will not be of that form. No, no, no. Uh, no, yeah, that's correct. No, I understand. Uh-huh. Yeah. Mm-hmm. No, this has the same problem. No, I understand. Yeah, this has the same problem, so it doesn't work. Uh, uh-huh. Uh-huh. Mm-hmm. Yeah. Then this will never work. Uh-huh. Then you can no. So I don't understand. So if you take A and A complement, and A is closed under addition. Yeah. Uh-huh. So yeah. So if A and B are in A, then A plus B by 2 is in A, right? And B also is like that. So let's write that. So both are closed under average. Right, that's better notation. So then A1 plus A2 by 2 is in A. Yes. Mm-hmm. Oh, but that we already said. Average of two things in A. Mm-hmm. But how can you find, okay, yes, if you can find this kind of sets, right? So you're saying the average is in A, right? So you're saying that you define it on this. So you define, no, but both are closed. No, 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 this can work, right? This, I mean, if you can find this kind of sets, uh, so you can define that, 1 minute. So you are the average is in, yeah, so you can define it like this, right? So you can define it to be 0, let's see if it works, on A, and you can define it to be 1 on B. Right? So if you're picking 2 points which are in A, then it works. If you 2 points in B, it works. But if you pick a point, one of them is in A and the other is in B, yeah. Let's see. Then this quantity is how much? It's half, right? But the average is in A, right? So it means that this thing is 0. Yeah. So if you can find these kind of set, I mean A and A complement like this, then it will work. Both have to be closed. Yeah, and that uh, mm-hmm, mm-hmm. Yes, you can come to that from outside. Yeah. Huh. Yeah. No. Why? Why? Because B1 is coming from outside, right? Two things from one from inside and one from outside. Can come inside. No, closed doesn't mean that it's closed from outside. Closed means that you take two things inside, then the average is inside. But you can take two things outside, rather, I should say, you could take one thing outside and one thing inside, and the average can come inside. That is not, that can happen. I mean, that we are not saying that cannot happen. That doesn't follow from here that it cannot happen. It can happen. But whether such things will exist, I don't know. What can happen, meaning that one thing from inside and one thing from outside, the average can come inside. Yeah, it seems strange, but I don't know if such sets will exist. But there was a, that is, but we have to make them complement. Otherwise, there's no point to the construction. Yeah, but no, but this is a true fact. So let me. I'm just checking it. Midpoint convexity. Uh, because you see, I have let's seen this. Clear this up. We don't want to. So where is this question? No, so it might be a very complicated. Uh, Oh, there's a very simple counterexample. Oh, sorry. Yeah, so I just looked it up. So okay, so I think that that should work. Well, so the let me just present it. So well, the idea is that you have to take. Let's see. I've just seen the example. We'll try to prove it. Okay. I'm not even seeing the example. So the point is that you take the function fx. You take a convex function. Okay. You take a convex function fx equals x squared. Start with a convex function, and you make it non-convex, something like that. Okay. Start with start with a convex function. Start with what was I saying? Start with this, and so then how do you make it non-convex, but keep it midpoint convex? Yeah, that's what we should be doing. So if you start with this and somehow make this non-convex, if you kind of redefine it at a few points, yeah, how do you do that? I don't know. You think? Yes. Am I on mute? No, I'm not on mute. Yes, yes. So then, so if we take this convex function, then how can we remove the convexity? So maybe what you can do is you keep it. Yes. So you keep it like this for the rationals. Okay. And then you kind of at the irrationals, you drop it. Okay. So, I mean, at the irrationals, you kind of irrational values, you drop it. So then why does this become, why does it remain midpoint convex? So that's the first question. Why? Yeah, that was a simple idea to start with this thing. So why is it midpoint convex? Let's think about that. So if you take two values, and why is the average less than that, or average of the values? So it's not going to be difficult if you just check it, right? But can we also see? Can take the average, and so if both are rationals, then it's fine. Yeah. If so, if two of them are irrationals, then it's also fine. So then it's just zero. But if one of them is rational, and one of them is rational, and the other is irrational, then also it is fine, right? Yeah. Sorry. No, no, no. If both of them are irrational, then it certainly works because this is a convex function. So that's what I'm saying. Both of them are rationals. It's a convex function, right? That's the whole point. Yeah. I mean, it's a convex function. So yes, yes, yes. That's right. But then it's that is the thing. Yeah. So something. But then does this work? Let's just check this. Yeah. First. So if let's do this step by step. Okay. So if A and B are both in Q, then this works because it's a convex function. And if A and B are in Q complement, sorry, because then it says 0, then it works. So no, but no, that's where it doesn't work, right? If both of them are in Q complement, then does it work? No, that doesn't work, right? Because it's big mess. Yeah. So yeah, that's what I'm saying. Yeah, it doesn't work. So then that's the problem. So if you take 2 plus root 3 and then you take the average, then it doesn't work. So it becomes irrational and it becomes whatever 4 or something. No, even then it doesn't work, even if the inequality is not strict. Right? Because again, the same problem as Sampath said, it has the same problem of the previous example. Of the previous example I was trying to make. Right? So yeah, so let me just think about this. This seems to be a mess. Yeah, you guys also think about it. I think this is true, but currently I'm a little tired to think. But I will think about this and tell you. No, it is no. It is true that midpoint convex doesn't imply convex. That is, we will certainly need continuity. Yes, yeah, and for that you have to. That is not easy to prove. Also, that's not trivial to prove. But that's you can think. Well, you can complicate it. Yeah, that's a complicated way to think about it. But essentially, you get a set of points. So no, the point is that you can get a dense set of points where so midpoint convexity implies convexity on a dense set of points. What is that dense set of points? The points in which the denominators are powers of 2. That you can show, right? Midpoint convexity implies that. Numbers of the form, that, and that's basically what they call it diagonal. So on a dense set, the inequality holds. So you could take limits, right? I mean, for any lambda, you can kind of understand. Okay. Yes, so I have made some error. Yeah, in thinking that this is simple. You're right. Triple point average, those kind of things. Triple average. I don't know. I don't know. And no, the others will also imply because all those uh, no. It doesn't work. I think I have to think because yeah. So that I don't know. I have to think. Yes. Uh-huh. In the limit you can reach. In the limit you can reach, right? Uh, so well, the point is that you can um, no. So the point is that show if you want to show this for all A and B, but no, it's not about A and B being diet. That is a misconception. It is, yeah, it is the lambda. It is having control over the lambda. So yeah, so you can, that is basically a take limits, right? So so it is this. Sorry. So basically, if you want to show it for some lambda, right, then you essentially make a sequence that tends to lambda. Okay. such that for every point in the sequence, the inequality is implied from midpoint inequality, from midpoint convexity. Okay, so basically my point is that you can take these numbers, you can take these AIs as summation 1 by 2 to the power 2 to the power k, some yeah. And you can take such sequences. This is a finite, yeah. Maybe I should do a double indexing, but let me not do that. Let's say from J to N. Okay, you understand, right? So you can take these kind of AIs. So first of all, you can take these kind of AIs and you can tend to lambda for any lambda. Okay, these kind, but that means the proof. No. Yes. So for that only I'm analyzing and seeing if I can say anything. Yes, that's right. So first of all, these kind of numbers are dense. Okay. So why is that true? Because you can use binary expansion of any number. Okay, so you have to think about that. Okay, given any number, if you take a binary expansion, then it's in you will be used to the powers of 2, but then when you have a number less than 1, then it's powers of half, right? So any number can be written as an infinite sum of powers of half, any number less than 1. Yeah? So for less than 1 also you can do something like that. Okay, basically it's very similar, yes, because basically you have to take, if you're taking a number x less than 1, you have to take the largest power of half that you can chop off from here, so that this is greater than 0. You take the largest just power of half, which you can take it off from this, and so that you cannot do with k minus 1. Okay, you see, it's like a greedy algorithm, and you keep taking these differences, and you show that the difference becomes smaller and smaller, it tends to 0. Okay, so then x in the limit becomes equal to that infinite summation. Okay. Or you can just show that every rational can be written like this as a finite summation, and then rationals can, but let's assume that you can. Okay, so basically my point is that every real number, can be written as potentially an infinite summation. Every number less than 1 can be written as an infinite summation like this. And that's what it means to say that these numbers are dense, right? Because it tend to it using these numbers. Right? Any number lambda can be written as an infinite summation, and then you can take the partial sums and that. Okay? So you can take these kind of AIs and you can tend to that. Now you have to show that using the midpoint convexity, you can, using midpoint convexity, you can show that so using midpoint convexity, you can show that for these kind of numbers, you can get 1 minus to do the same thing. You have to use midpoint convexity, which is only given for a plus b by 2. You can show that you have to show that you can use that to prove for this. Okay, you can write the rest. Okay, so from midpoint convexity, you have to prove this, and then because these are dense, you can take the limit as j goes to whatever ai goes to. So what I'm saying is that we have shown that this aia plus 1 minus aib is bigger than, and for this, yeah, you may have to use induction. So you theoretically extend midpoint convexity to this case, and then you can take the limit and you can do it. Now, if you take triple one, then that I am not sure, because for that one. So if you, when you try to prove this, that midpoint convexity implies this, then you will realize if you can do it for 1 by 3. Okay. Because because if you want to reach any real number lambda using powers of 1 by 3, you cannot do it. You have to use powers of 1 by 3, but you have to also use this maybe coefficients 2, or that coefficients you can also have your closure change. Is that right? Yeah, because if you take a base 3 expansion, then the coefficients can be 0, 1, or 2. Only with 0 and 1 you cannot reach every real number, right? Every integer you can, if you want to use that. So then you have to see, you will get, if you're using, you have to see if you can get 2 and 3 also. So you have to see if, basically it's simple, you have to see if a triple point convexity will imply something like this. Will you be able to show that triple point convexity implies this? So 1 minus, will your triple point convexity imply this? Because you will need numbers, not just powers of 1 by 3, but powers of 1 by 3 potentially multiplied with 2 or 1 arbitrary. Whether you can do that, I don't know. You can try to check it. Try to do that. So let me just stop here for today. Okay. Yeah. So this mock test discussion was not very good today, but I will continue this tomorrow. Okay. So if those of you who want can attend this. So I'll continue tomorrow. Tomorrow I'll do at 9. Okay. I will try to do the rest of the questions. Yeah. Sorry. It's a bit late. So I mean, and.